So, my dear students, in the last period, we have seen that oxidation means loss of electrons by any species, reduction means gain of electrons by any species, oxidizing agent is the acceptors of electron or electrons or substance that is reduced during the redox reactions, whereas reducing agent is the donor of electrons or the substance that is oxidized. Now, let's move forward and understand. We have a question. Justify that the reaction 2Na plus H2 that gives 2NaH is a redox change. Since the above reaction means the reactions between the sodium metal and hydrogen, since the above reaction, the compound formed is an ionic compound, which may also be represented as Na plus and H minus solid. This suggests that one half reaction in this process is 2Na that gives 2Na plus 1 plus 2 electron. And the other half reaction is H2 gets 2 electron to produce 2H minus. So here you can get 2H minus in the gaseous form. This splitting of reaction under examination in two half reactions automatically reveals that here sodium is oxidized and hydrogen is reduced, and therefore the complete reaction is a redox change. Now, my dear students, we want to study about the competitive electron transfer reactions. So there is a competition between the transfer of electrons. Let us see how and understand it well. Place a strip of metallic zinc in the aqueous solution of copper nitrate for about 1 hour. We may notice that the strip becomes coated with the reddish brown metallic copper and the blue color of solution disappears. Once again, we need to put a zinc strip into the copper nitrate solution and we'll have to keep it for an hour. After an hour, we'll observe that the blue color solution of copper nitrate has lost its all color and it becomes transparent, or the color blue color of copper plus 2 ion disappears. And you can see that on this zinc rod, there is a deposition, Cu copper deposited on the zinc color. You can see even clearly into this figure that even I have tried to make the color as good as the color of copper. So here you can see that in the initial stage, we put a zinc rod deep into the copper nitrate aqueous solution, which was blue in color. After some time into the intermediate stage, the intensity of color is reduced. From dark blue, it turns out to be light blue. And at the end of the reactions, finally, this blue color has been disappeared and there is a deposition of copper on the zinc rod. Formation of Zn plus 2 ions among the products can easily be judged when the blue color of solution, which was due to the Cu plus 2 ion, disappears and when copper is deposited on the zinc rod. If hydrogen sulfide gas, that is H2S gas, is passed through the colorless solution containing Zn plus 2 ions, white precipitates of ZnS are produced, confirming the presence of Zn plus 2 ions. So, my dear students, when we look into the figure once again, when we put this Zn zinc rod into the CuNO3 twice solution, what happens? This zinc reacts with CuNO3 twice and produces ZnNO3 twice. And Cu turns out to be solid. So here in ZnNO3 twice, my dear students, we have Zn plus 2 ions. So in this transparent solution, we have Zn plus 2 ions present into it. These Zn plus 2 ions are precipitated when we pass H2S gas and we get ZnS And these ZnS are the white precipitates. So we get white precipitates of ZnS. Once again, I should read it for you. If hydrogen sulfide gas, that is H2S gas, is passed through the colorless solution containing Zn plus 2 ions, white precipitates of ZnS are produced, confirming the presence of Zn plus 2 ions into the colorless solution. ZnS can be seen by making the solution alkaline with ammonia. So if the precipitates are not formed properly, we need to add some of the NH4OH, which is actually the solution of ammonia that is formed by the reaction of NH3, which is dissolved into the water. So when NH3 gas, ammonia gas is passed through the water, we get NH4OH. And if we add NH4OH to this solution, the solution become alkaline, that is basic in nature, and we easily get the precipitates of ZnS, that is zinc sulfide. The reaction between metallic zinc and the aqueous solution of copper nitrate is written over here. You can see that I have already written these reactions for you, that ZnS, zinc solid, reacts with the copper plus 2 aqueous ions, and thus zinc plus 2 ions have been produced and copper is deposited as a solid on the zinc rod. In the above reaction, zinc has lost electrons to form Zn plus 2, so zinc is oxidized. So in the above reaction, we can easily understand that zinc from Zn solid turns out to be Zn plus 2. So zinc has lost 2 electrons, and that is why zinc is being oxidized. Evidently, now if zinc is oxidized, releasing electrons, something must be reduced. So accepting the electrons that has been released by zinc, accepting the electrons lost by zinc, copper ions are reduced to copper metal. So we can easily see here that zinc solid released 2 electrons and turns out to be zinc plus 2 ions. These 2 electrons which are released, they are gained by copper plus 2 ions, gain 2 electrons and turns out to be copper solid. So if we really compare zinc and copper, then we can say that in competition of releasing electrons, zinc is more powerful in releasing electrons, and that is why zinc releases electrons when it comes in contact with copper, whereas copper is less powerful in releasing the electrons, and that is why copper plus 2 ion accept these electrons and thus gain these 2 electrons, and they are being reduced. But now if you put the copper strip to the zinc sulfate solution, if we take Cu and ZnSO4, then there will be no reaction, my dear students. No visible reaction takes place. Even passing the H2S gas does not produce black precipitates of CuS. So when copper strip is put into the zinc sulfate solution, when compare the ability of copper to release electron, zinc has got more ability, and that is why copper does not release electron in the presence of zinc. But now we can do one more thing. Let's place copper strip to the silver nitrate solution. But instead of zinc sulfate, if we put the copper strip into the silver nitrate solution. Now here you can see the figure on your screen, my dear students, that we have this silver nitrate solution. You can see the silver nitrate solution. We have put the copper strip into it. In the initial state, there is no blue color. As the time passes, the uh, uh, in the intermediate state, the blue color start appearing and blue color start developing. So it is a light blue color, and finally, when the reactions get over, silver is deposited on the copper strip. You can see easily the deposition of silver on the copper strip at the final stage, and the intense blue color of the solution has been developed. Thus, we can see that the solution develops blue color due to the formation of Cu plus 2 ions and due to the redox reactions. So I hope, my dear students, you can easily understand that this copper, which was a solid, when it reacts with the 2 Ag plus ions, which are present into the aqueous solution, this Ag plus or this copper loses its electron and forms Cu plus 2, and these electrons which are released by copper are gained by Ag ions, and these Ag plus 2 ions turns out to be 2 Ag solid ions. So here if you look at the copper, by the loss of 2 electron, copper is oxidized, whereas by the gain of 2 electron, my dear students, you can easily see here, by the gain of 2 electrons, this silver is reduced. So this is how we can easily understand the reactions. Let's move forward and understand it well. You can see here the same reactions I have written here, that copper releases 2 electrons and turns out to be Cu plus 2. Silver gains these 2 electrons and turns out to be silver solid. Here copper solid is oxidized to Cu plus 2 aqueous and Ag plus aqueous is reduced to Ag solid. Equilibrium greatly favors the product Cu plus 2 ions and silver solid. So at equilibrium, we can easily come to know, or we can have the various evidences. On the basis of that, we can say that Cu plus 2 ions are present. Generally, the color, the blue color of solution indicates that Cu plus 2 ions are present, and we can visibly see the deposition of silver on the copper strip. When metallic cobalt is placed in the nickel sulfate solutions. Now let's look at this. When metallic cobalt is placed into the nickel plus 2 solutions, here I need to write plus 2 actually, Ni plus 2 aqueous solutions. So when cobalt is taken, cobalt strip is placed into the Ni plus 2 solutions, we get cobalt plus 2 and Ni solid. So cobalt actually releases 2 electrons and nickel actually gains 2 electrons and turns out to be nickel solid. Now when we look at these reactions at equilibrium, suppose there is an equilibrium established between these two forward and reverse reactions. At equilibrium, chemical test reveals that both Ni plus 2 and Co plus 2 are present at the moderate concentration. So during these reactions, in this case, my dear students, we can easily understand that in this case, neither reactants, that is cobalt and Ni plus 2 aqueous, nor the products, that is cobalt plus 2 and Ni solid, are greatly favored. So when we study these reactions, or when we put the cobalt strip into the aqueous solution of nickel plus 2 ions, we can easily observe that when the equilibrium is established between the forward and reverse reactions, we have all these 4 species present almost equally. So none of the reaction completes, and the presence of Ni plus 2 ions as well as the Co plus 2 ions are observed at the equilibrium. And thus neither the forward reactions, that is the oxidation of cobalt to cobalt plus 2 ion, or the reverse reaction, that is the reduction of cobalt to cobalt plus 2 ion, or the oxidation of nickel to nickel plus 2 ion is favored. Both the reactions, or if we compare the ability of cobalt and nickel, we can say that both cobalt and nickel have similar ability to lose electron. They have similar ability to release electrons. Thus, if we compare the various metals, we come to know that these various metals have various kinds of ability to release electrons. Some metals have high ability to release electron, for example, zinc. Some metals have low ability to release electron, for example, silver. Some metals have almost equal ability to release electrons, for example, cobalt and nickel. So this is how, my dear students, if we really study, we can arrange the various elements or various metals in the ability or in their ability to release the electrons. We observe that we have elements, those have competition to release electrons, and thus one element can displace other. For that we study order of activity. So from all this, we can conclude that zinc has a more possibility of releasing electron than copper, and copper has more ability to release the electron than the silver. So we can arrange them in the decreasing order of their ability to release electrons. Using this, we made metal activity series, and that we already have studied into the 10th standard. The competition for electrons between various metals help us to design a class of cell named galvanic cell, in which chemical reaction become the source of electrical energy. So once again, my dear students, I would like to remind you that the cell which is known as the galvanic cell, we can prepare such galvanic cell using the various metals which have different ability to release electron, and these galvanic cells are used to produce the electrical energy. In this galvanic cells, the chemical energy is being converted to the electrical energy. When various elements are tried to see their ability to release electrons, they are arranged in the increasing order of their ability to release electrons, and a series of the elements formed. This series of elements formed is known as the electrochemical series. So on the basis of the ability of various elements to release electron, either they are metals or non-metals, they are arranged in the increasing or decreasing order of their ability to release electrons, and thus the series of element has been produced, and this series of element is known as the electrochemical series. So this is how we study, or we may study about the electrochemical series. Now, my dear students, we want to study about a very important portion, that is what it is known as the oxidation number. Let us study about oxidation number. What is oxidation number? In the reactions 2H2 plus O2 that gives us 2H2O, actually hydrogen oxidizes by the loss of 4 electrons to water, oxygen reduced by the gain of 4 electrons to water. So here in the above reactions, we realize that hydrogen atom is going from its neutral state in H2 to positive state H2O. That is 2H2 that gives 4H plus 4 electron. Same way the oxygen atom goes to the di-negative state in H2O from its neutral state O2. So O2 gains 4 electron and turns out to be 2O minus 2. It is assumed that there is an electron transfer from hydrogen to oxygen. It is believed that the electrons flows from hydrogen to oxygen. However, the charge transfer is only partial, and it is better described as an electron shift rather than the complete loss of electron in a covalent compound. Now, this is an interesting as well as important point. Generally, what do we believe? If there is an ionic compound, these ionic compounds are ionic compound because they have ions, and ions are the charged species. So these ionic compounds have ions, they have force of attraction, which is known as the electrostatic force of attractions, and they exist as ions. But as far as the covalent compounds are concerned, my dear students, there is no exactly the transfer of electrons. But instead of the transfer of the electron, we can consider them as an electron shift. So electron which was near to one nucleus goes near to the another nucleus, but there is not actually the exact transfer of electrons as far as these covalent compounds are concerned. To understand this shift of electron, to understand the electron shift in a covalent compounds during chemical reactions, a more practical method called oxidation number has been developed. Now please remember that this oxidation number has to be developed just to understand the position of the covalent compound, or to understand how these various redox reactions takes place involving the covalent compounds. So let us study about the oxidation number and oxidation method. In this method, how the electron transfer takes place into the covalent compound, in this method, it is always assumed that there is a complete transfer of electron from a less electronegative atom to a more electronegative atom. Though it is very clearly understood that there is not a clear transfer of electron, but to understand these processes, it is assumed, my dear students, that there is a complete transfer of electron from from more electronegative element to the from less electronegative element to more electronegative element. So more electronegative element takes electron and turns out to be negatively charged, and less electronegative element loses electrons and turns out to be positively charged. To express the oxidation number, we write the chemical reactions and show charges on each of the atom forming part of the reactions. For example, if you look into the reactions, 2H2 plus O2, that gives 2H2O. We have hydrogen into the zero oxidation state. We have oxygen into the zero oxidation state. But in a covalent compound H2O, we have hydrogen is in +1 oxidation state and oxygen is in -1 oxidation state. Same way into H2 plus Cl2, the hydrogen and oxygen in the reactant side, they have zero oxidation number, but in HCl we have hydrogen has got +1 oxidation number and chlorine has got -1 oxidation number. Same way when we look into the reaction CH4 plus 4Cl2, that gives CCl4 plus 4HCl, we can see that in methane we have hydrogen with +1 oxidation state, carbon with -4 oxidation state, chlorine has got 0 oxidation state. In CCl4, carbon has got +4 oxidation state, chlorine has got -1 oxidation state, and hydrogen has got +1 oxidation state, and chlorine had got -1 oxidation state. So my dear students, this is how we understand, or this is how we represent the chemical reactions by using their oxidation state into the particular covalent compound. Please remember that the assumption of electron transfer is just for the purpose of bookkeeping. Bookkeeping means maintaining an account so that we can understand how the electrons can be transferred. There is no actually transfer, but just to maintain the record, just to understand it mathematically, just to understand it, how does it take place, or it is just for bookkeeping. The actual transfer is not possible. So please remember that the assumption of electron transfer is just for the purpose of bookkeeping, to understand the chemical reaction better only. Just to understand the chemical reaction better, actually the reaction does not take place by the complete transfer of electrons. Electrons are partially transferred, not completely transferred into the covalent compounds. Please remember that electrons are just partially transferred, not completely transferred into the covalent compound. Oxidation number denotes the oxidation state of an element in a compound ascertained according to a set of rules for mutated on basis of the electron pair in the covalent bond. So oxidation number denotes the oxidation state of an element in a compound ascertained according to the set of rules formulated on the basis of that electron pair in a covalent bond is completely transferred. The electron pair in a covalent bond has been belongs entirely to the more electronegative element. Let me read it once again for you, my dear students, that let me read it once again for you. Oxidation number denotes the oxidation state of an element in a compound ascertained by according to the set of rules formulated on the basis that electron pair in a covalent compound belong to the more electronegative element. It belongs to the more electronegative element. Now let us understand it word by word. See, we put oxidation number that represents the oxidation state of an element. How do we put this oxidation state? We put it by using some of the laws. We put them by using some of the rules. which are formulated on the base, and these rules are formulated believing that the more electronegative element has got this electron pair with it. Because it is more electronegative, it must have the electron pair, or it has attracted the electron pair towards it, and that is why it is negatively charged. So we give oxidation number, and we give oxidation number according to some of the rules that we are going to study, and these rules are formulated in such a way that we believe that the electron pair is present on the electron pair belong to entirely to the more electronegative element. So whenever we give the oxidation number, we believe that the electron pair belong to the more electronegative element, and whenever we give these numbers, we give this number according to some of the rules that we are going to study. If two or more than two atoms are present of a particular element in a compound or in a polyatomic ion such as Na2S2O3 or Cr2O7-2, the oxidation number of the atom of the element will then be average of the oxidation number of all the atoms of the element. Please understand this. It is very interesting for us to know this. If two or more than two atoms are present of a particular element in a compound or in a polyatomic ion. So this is the particular compound and this is the ion. You can see that here we have sodium, sulfur and oxygen, three element present. Here we have chromium and oxygen, two element present. The oxidation number of the atom, suppose we want to determine the oxidation number for sulfur. So this oxidation number of the atom sulfur, that element will then be average of the oxidation number of all the atoms of the element present into it. So here you can see that we have two sulfur present into it. That means the oxidation number of each sulfur is the average of the oxidation number of these two atoms of sulfur. If we want to determine the oxidation number of oxygen into Cr2O7-2, then this oxidation number of any oxygen is actually the oxidation number of, or is actually the average of the oxidation number of all these 7 oxygen present into Cr2O7-2. So my dear students, when we determine the oxidation number for any element and ascertain it, we are actually writing the average oxidation number for that particular element in a polyatomic ion or polyatomic compound. It is not always possible to remember or to make out easily in a compound or ion which element is more electronegative than the other. We have huge amount of compounds available for our study. So it is not easy to remember the electronegativity for all the elements present into the compounds. So we have different elements and they have different electronegativity, and we ourselves cannot remember all the electronegativity for all the elements. And for that, what do we need to do? Therefore, a set of rules has been formulated to determine the oxidation number of an element in a given compound or in a given ion. So as we cannot remember all the electronegativities for all the elements, we will have to define some certain rules, and on the basis of this rule, we ascertain or we provide the oxidation number to any element in a given compound. Following are the rules for calculating the oxidation number of element present in a compound or ions. So my dear students, now we want to study those important rules for ascertaining the oxidation number for any compound. Let us study these rules one by one. My dear students, am I audible? Can you hear me? Dear students, can you hear me?
Yes.
Okay, thank you. Let's move forward. So the first rule, the charge on the fluorine is always -1. Please remember that we will always keep the charge on fluorine as a -1. The charge on all alkali metals is always +1, whether it is lithium, sodium, potassium, rubidium, cesium or francium. the charge we will always keep +1. The charge on all the alkaline earth metal is always +2. That means if we have beryllium, magnesium, calcium, strontium, barium or radium, they always have +2 oxidation state. Whether they are bonded with the oxygen, whether they are bonded with the hydrogen, or whether they are bonded with the any other element. These three rules are never changing and they are always, they contain the word always with them. So once again, the oxidation state of fluorine will always be -1. The oxidation state for lithium, sodium, rubidium, cesium and francium will always be +1. The oxidation state of beryllium, magnesium, calcium, strontium, barium and radium will always be +2. There is one more rule like always, and that is aluminium Al is always having the oxidation state +3. So Al is always Al +3. Please remember. So now these four rules are for always, and this is what it helps you to determine all the other elements and their oxidation state. Let me repeat once again. Fluorine will always have -1. Charge lithium or oxidation number lithium, sodium, rubidium, cesium, francium will always have +1 oxidation number. Beryllium, magnesium, calcium, strontium, barium and radium will always have +2 oxidation number. Aluminium will always have +3 oxidation number. Now on the basis of this four rule, we can determine what kind of compound it is and what could be their electronic or their oxidation number. Charge on oxygen is generally -2. But there are many exceptions or there are few exceptions. But it may be -1 or -1/2 if it combines with the alkali metals or alkaline earth metals, depending upon the oxidation number of the metals, alkali metals or alkaline earth metals bonded to them. For example, in Na2O2 or H2O2, oxygen is -1, which is called the peroxide ion. In superoxides like KO2, CSO2, or RbO2, the oxidation number for oxygen is O -1/2 or O2 -1, which is called superoxides. But now if you remember that rule that sodium will always have +1 and potassium will always have +1 or cesium will always have +1 or rubidium will always have +1, you can easily identify that here the oxidation state of oxygen will be -1 and here the oxidation state of oxygen will be -1/2. Because the total charge we will consider as 0. So for cesium is +1, then for O2, for complete O2 we will have -1. Same way for sodium it is +1, Na2O2, so oxygen it will be -1, that we can easily understand. So if you know these four rules which I have told you first, then it will be easy for you to ascertain any oxidation number. Sometimes oxygen gives positive oxidation number even. So positive oxidation state of oxygen is possible with fluorine only. Please remember that oxygen can give positive oxidation state with fluorine only. So if you look into the OF2, the oxidation state of oxygen is +2. If you look into the O2F2, the oxidation state of oxygen is +1. If you look into the HOF, the oxidation state of oxygen is 0, my dear students. Though it is a compound, the oxidation state of oxygen is 0, hydrogen has got +1 and fluorine has got -1. Let's move to the sixth rule, my dear students. In a free or uncombined state, each atom bears an oxidation number of 0. So if in a reaction we write O2, Cl2, O3, P4, acid, sodium, magnesium, aluminum, copper, these all are ascertained the oxidation number 0. For ions composed of atoms, oxidation number is equal to charge on ion. So my dear students, if we have Mg+2 ion, then oxidation state is +2. For Fe+3 ion, the oxidation state is +3. For Cl- ion, the oxidation state is -1. For O-2, oxidation state is -2. Eighth rule, my dear students. The oxidation number of hydrogen is generally +1. But when it combines with the metals, its oxidation state is -1 called hydride. So when we have lithium hydride, sodium hydride, calcium hydride, aluminum hydride, you can see that all this hydrogen has got -1 oxidation state. So please remember, my dear students, that the oxidation state of hydrogen can be minus. And when it combines, especially when it combines with the alkali metals or alkaline earth metals or aluminium, its oxidation state is going to be -1, because hydrogen is more electronegative than all these metals. Sometimes the oxidation state of hydrogen can also be negative when it combines with carbon. Please remember this sentence. Then, my dear students, if we think about chlorine, bromine and iodine, chlorine, bromine and iodine have generally the -1 oxidation state. But when chlorine, bromine or iodine combine with the oxygen, please remember, when chlorine, bromine or iodine combine with the oxygen, or if they are present in the compound containing oxygen, they show positive oxidation state. Same way, my dear students, there are some compounds which are known as the interhalogen compounds. Please remember that there are some compounds which are known as the interhalogen compounds. In these interhalogen compounds, we always have F will be minus. So if you have BrCl, or if you have BrF3, then here bromine will have +3 charges, or BrCl, then bromine will have +1 and Cl will have -1. So those elements or those halogens which have more electronegativity, they will have negative charge, and those electrons, those element or those halogen which have less electronegativity, they have plus charge. Even, my dear students, IF7 is also possible, where fluorine has got -1 oxidation state and iodine has got +1 oxidation state. So in the interhalogen compounds, the halogen will have the positive oxidation state, except fluorine. Fluorine will never have positive oxidation state, or when halogens are bonded to the compound containing oxygen, or they are just bonded directly to the oxygen, this halogen may have the positive oxidation state. Now, next rule, my dear students, that is the 10th rule for a compound. The algebraic sum of oxidation number of all the atoms in a compound must be 0. For example, if we think about hydrogen chloride HCl, oxidation number of hydrogen plus oxidation number of chlorine is equal to 0. So for any compound, if we think, then the algebraic sum of all the elements, the algebraic sum of the oxidation number of all the elements present into the compound should be 0. Same way, my dear students, for polyatomic ions, the algebraic sum of all the oxidation numbers of atoms of the ions must be equal to the charge present on the ion. So for CO3 minus 2 ions, or for carbonate ion, my dear students, we can write that the sum of the oxidation number of 3 oxygen and the oxidation number of 1 carbon must be -2. So we can write that oxidation number of carbon plus 3 multiplied by the oxidation number of oxygen is equal to -2. So this is how, my dear students, these are the 10 various rules on the basis of which we can understand how we can ascertain the oxidation number to the various compounds. I hope, my dear students, you have enjoyed your studies. Now, if you have any doubt,